Now let's give a big hand to Professor B.
Okay. Welcome everybody to my talk. It's always a pleasure to attend this nice meeting, and I hope I can contribute in person in the future again. So today I will talk about efficient processing of semiconductor, and let me now skip the outline and start with a small motivation. I got this slide from Infineon. The business growth in the semiconductor market is actually driven by 4 areas. It's energy efficiency, it's mobility, security, and IoT and big data. So finally, we can conclude the semiconductor market is constantly growing, and laser technology is a very promising technology for machining of semiconductor materials. And especially ultrashort pulses lead to higher machining quality, but efficiency and throughput still represents some issues, and these issues has to be solved. And that's why I'm talking today about silicon machining with ultrashort pulses. So maybe very short what we did. We used different laser systems. We guided the beam through via mirrors and the telescope onto a scanner, and then we machined here our silicon target. I will today present you experiments from 2 laser systems. It's a 10 picosecond system in IR and in green, and it's also a femtosecond system with 280 femtosecond pulse duration in the near IR. So just to be complete, if we worked with the 10 picosecond system in IR, our spot size was about 10.4 micrometer or 15.5, depending on the objective we have used here. When we went to the femtosecond system, we had 10.4 or 16.2, again, depending on the objective we have used. And for 10 picosecond systems, we have also made some experiments in green, and there the spot was very small with the radius of 7.2 micrometer. And what I want to show you today is results from silicon, mainly from 100 oriented silicon, but then I can also show you some results from 110 and 111, which gave for me some surprising results. So let's start. First, we investigated pulse bursts on silicon. What is a pulse burst? You see here the situation. You have your single pulses with the given repetition rate, and when you are using bursts, you distribute your energy of 1 pulse here among, for this example, 2 pulses, or here 4 pulses. And this is a burst, and the intra-burst time delay between these pulses is very short, mostly between 10 and 25 nanoseconds. So what is the advantage of this technology to use bursts? Of course, you can lower the energy of a single pulse when you use a burst sequence. And you see here, this energy you had in 1 pulse is the same in this burst packet, but the energy of each pulse is only 1/4. So you can lower the energy if you need it. And the other thing is, if you would use the same energy per pulse, you will, of course, increase the average power you're using. So this is what you can do with bursts. And now I will show you the removal rates we get with the IR 10 picosecond bursts from single pulse up to 14 pulses per burst. And you see when you go maybe to an average power of 35 watts, you can remove up to 6 cubic millimeters per minute with bursts of 8, 10, or 14 pulses. So high number of pulse bursts allow to use higher average powers at identical individual pulse energies, I have shown before, and lead to high remove rates up to a few cubic millimeters per minute. But when you now calculate not only the removal rate, but the efficiency, how many material you remove per energy you put in, the situation changes a little bit. You see that you get very efficient with the high number of pulses per burst. This is the point with the highest efficiency. This is the corresponding fluence, which is directly scales with the pulse energy. So, and you see this efficiency increases with the number of pulses per burst. And the fluence, or which means the pulse energy, where you achieve this optimum point, is shifted to lower values. So, but anyway, we can expect higher efficiencies for higher number of pulses per burst. And you can see here that you can increase the efficiency by about a factor of 4 when you go from single pulses to this 14 pulses per burst. So when you go to femtoseconds, also in IR, here only up to 8 pulses per burst, because this was the limit of the system. You see again, okay, you start here with 1 pulse, then you lose a little bit of efficiency when you go to 2 pulse burst, but then it increases for 3, goes a little bit down for 4, and then for 6 and 8, you get again up and you achieve quite high values. So we increase also the specific removal rate for higher number of pulses per burst, which means here the energy efficiency. And in principle, you get similar maximum values compared to 10 picoseconds from about 4 pulses per burst on. So there is not a big difference in the efficiency finally. The tendency where you get this optimum points is not so clear as for 10 picoseconds, but we can see here it's of course at higher values. If you compare this, where you have your optimum somewhere below 1 joule per centimeter, you are here about twice as high, so you can use higher average powers. So now when you go to green, the situation changes a little bit. You see here again 1 pulse per burst, 2 or 3 pulses per burst, and there is no big difference. So it does not matter if you have single pulses, 3 pulse bursts. Unfortunately, we were not able to go higher with the number of pulses per burst. But what you can see is that you are more efficient compared to IR. You get here values of about 3 cubic micrometers per microjoule, and when you compare this with the femtoseconds, okay, or with the picoseconds here, you are lower. So, optimum peak fluence is also shifted to higher values. This is maybe important. So let's have a look onto these green results. You see here the results for single pulses. This is the surface of the silicon we machined. Each row has the same fluence per single pulses in the burst, and 2 pulse bursts, 3 pulse bursts, and you see in case of bursts at low fluences, you have some shiny surfaces, very nice. But what you have seen before, the optimum peak fluence is shifted to higher value. The surface is again still back. And what you see here is for 1 pulse, you have a quite high surface roughness with 1.4 micrometer, and then it drops down below 500 nanometer for 2 and 3 pulses per burst. So you have a strong difference in roughness. So, but anyway, what can we do? We had this very small project with Infineon and NextScan where we wanted to use this higher efficiency of bursts, because if you dice small wafers, you can see that the mean die break strength increases when your fluence decreases. So it's better to go into this direction. And then we wanted to check if we can achieve a good quality and also a high throughput with ultra-short pulses by using bursts and a fast scanning device, which is in our case here a polygon line scanner. So, and what you see here is the final result, what we got from this dicing technology. This is a 50 micrometer thick silicon wafer, and you see the quality finally is quite good. Sorry, what we have to do is we have to apply some special technology, which is called interleaving, which means you're scanning very fast so that the spot separation of your burst sequence is really more than 1 diameter, and then in the next pass you go exactly between, and so you can distribute the temperature a little bit better, and you have less melting effects. So this finally worked, and we got a very high quality with acceptable throughput for these dicing applications. So now let's go back to single pulses, no bursts anymore, and see what is the influence of the crystal orientation. Most silicon wafers are 100 oriented, and you see here again this specific removal rate, the efficiency as a function of the peak fluence or the pulse energy. And what you see here is that you have a drop in this region of about 1.5 joule per square centimeter, and then goes up. And when you measure the roughness for each square, you see the roughness increases, and then exactly in these regions, it drops down to very low values. So it seems as we have two regimes, one with the high roughness and one with the low roughness, and we have an interchange between. So let's go into this interchange. Let's take this value with the highest roughness, then this, and look how the surfaces looks like when they are machined. What you see here now are some videos, and you see the left one belongs to this fluence, the middle, the one in the middle to this, and the one at the end to this. And then you see what happened when you're now machining the surface. At low fluence, it is covered by cavities. If you increase the fluence only a little, the cavities are reduced, and finally they fully disappear. So that's what happened. So small melt film seems to be responsible for the smoother surface at higher peak fluences. We have a melting effect. This was for 10 picoseconds in IR. When we go now to femtoseconds, you have to apologize. This is not a picosecond, this is a femtosecond laser, 320 femtoseconds. So then you see the behavior is different. The specific removal rate increases and stays almost constant, and the surface roughness increases. There is no interchange and goes to high values. What you see here is now the surface you finally obtain after maybe 200 passes. And now we increase the pulse energy or the peak fluence, and look how this surface behaves. And you see it's getting worse and worse, rougher and rougher. You produce cones, and finally you end up in this very bad surface quality. This is what happened with femtosecond pulses. So you have no transition for femtoseconds in IR. When you go to green again and 10 picoseconds, where we had this interchange for IR, we have similar behavior. The surface roughness increases and then goes down below 500 or below 200 nanometers even. So the maximum specific removal rate almost doubled compared to IR. We have E3 compared to IR, where it is about 1.5. And again, we have this transition to a small surface with melt film as we observed it for IR. So, but we do not see two leading regimes in the removal rate. There seems to be no big difference. So now let's go to other crystal wafer orientations. What I have shown you now was all done with 100 orientation. Then we also machined wafers with 110 orientation or with 111. So we used the undoped wafers, all with the very low surface resistance. And now we will see what happens. These were the results I already shown you for IR in 100 orientation. And when you now go to 110 or 111, you don't have this interchange or this transition anymore. It goes up, it stays high, as we have observed for femtosecond pulses. So even if you change the spot size, maybe you change a little bit the efficiencies, but the general trend is still the same. You have this transition for the 100 oriented wafer, and again, no transition for the other two orientations. So, and even when you measure the surface roughness, it's the same. You have this transition for the 100 wafer and an increasing roughness for the other two orientations, as we have seen it for femtoseconds, also for the other one. So, and here again, pictures. You see that's a regime where we are rough, and then for 100, you get to this shiny surface where you have a low surface roughness. Again, in the row, there's always the same fluence per single pulse and you see for the 110 and the 111 orientation, this transition is not appearing. So, and also when you make this in situ microscopy, as I have shown you before, you see here now the 100, 110, and 111 at the same peak fluence. This is one below this point, maybe somewhere around here. And you can see what happens. At the end, the surface looks equal. So low peak fluence, low energy always leads to this bumpy surface. Maybe the 100 orientation leads earlier to this cavities than the other two. And now when you go to a higher fluence, so where we are above this transition, then you see that for the 100 orientation, this cavities doesn't appear anymore compared to the other two orientations. So, but when you now go back to bursts and make the same experiments, here just an example with the 5-pulse burst, this difference between the orientations vanishes. So there is no difference between the different crystal orientations, also not from the surface roughness, which means when you go to bursts, then you again have the same situation for all 3 orientations, and the final surface looks equal. Again, you see here a sequence of pictures from microscopy, and you see there is absolutely no difference when you use bursts. So let me conclude my talk. I have shown you the burst mode on silicon. In IR, you have significantly increased specific removal rates, both for picoseconds and for femtoseconds. Green shows you more metallic behavior, but smaller surfaces with the 2 and the 3 pulse burst. We have a minor influence of the crystal orientation, as I have shown you exactly at the end of the talk. And with bursts, we were able to optimize the dicing process for thin wafers. If we go to single pulses, then on 10 picoseconds in NIR, then the influence of the lattice orientation is very strong. For the 100 oriented wafer and 10 picosecond pulses, we have a smoothing effect. And with this, I will conclude, and thank you very much for your attention. Thank you.
Thank you very much.
So, in his experiment, he talks about 2 different things: single pulse laser and the burst pulse. It's a kind of combination of different types of the pulses with very interesting findings in the experiment. And any questions from the audience for Professor Neuenschwander? Any questions?
Can you hear me?
I can hear you.
Okay. Because you have used 2 kinds of laser. One is a burst type, the other is a single pulse. Do you think it is possible now for you to apply your burst mode laser in a real, for example, semiconductor industry?
Sorry, can you repeat the question?
Do you think it is possible or not for you to use the burst mode in the real semiconductor production line?
Yes, I strongly believe, yes. I think for some applications, as this dicing application, you really gain when you use bursts. You can use more energy, more average power, but reduce the energy of the single pulses and get better qualities compared to if you only use single pulses. I think this is possible, yeah.
about I think I have my own experience. About 15 years ago, I have made so many experimental and theoretical simulation on the burst mode. I think the most important things is the time duration between the two adjacent pulses. Two adjacent pulses is the time duration. What about the time duration in your experiment? For several nanoseconds? Or
Yeah, the interburst delay we used, it was in 10 picosecond case was 12 nanoseconds, and in the femtosecond case, it was 15.5 nanoseconds. This is not a big difference. We have also some experiments with the so-called gigahertz bursts. When your distance between the burst pulses is only 180 picoseconds or something like that. There, I don't know exactly. You get also high removal rates, but you have a lot of melting effects, and you can avoid this a little bit when you go to higher burst pulse distances. So, but for me, the picture there is not really finally clear.
because the pulse width is just 10 picosecond. I think it's a very short one, and the peak power density during your experiment will be, I think, somewhat high. Do you think there is a damage for you to use in some dicing process, stairs dicing? Yeah, I mean, SD process.
We made a lot of experiments for this dicing. If your pulse energy and therefore the intensity is too high and the peak power, you have a lot of side effects which lowers the quality. If your repetition rate or your pulse-to-pulse distance is too small, you have heat accumulation effects, also again lowering the quality of the dicing process. So you have really to find regimes where your pulse energy is not too high, your distance is high enough, and so on. So it's really finding a good regime for working. But if you have it, you can really be much faster than when you apply single pulses.
Okay. Okay. Wait for a few seconds.
So you can help me for the translation. So for this experiment, is very interesting study for different pulses and wavelengths, the effect on the silicon dicing. I would like to ask, you have done for IR and green. Do you have any shorter wavelengths, like for the UV? Have you done any experiment for UV?
You have told us you have carried out so many experiments by using your burst mode laser, by using the lasers with the wavelengths of 1 micron or 532 nanometers. And have you any experiments by using a UV laser? Ultraviolet laser until now?
We have experiments with green. This I have shown you, but not with UV.
You have.
If you think on silicon, yeah, of course. I mean, already green is maybe the photon energy is twice the band gap, and when you go to UV, it's even higher. So maybe the results could be different. But when you want to use the burst mode, then you have to have in mind that every frequency conversion process leads to a loss in energy. And when you divide to bursts, then the conversion efficiency may be even lower. So for our system, it's not so easy to go to UV and to bursts at the same time. But single pulses UV, yes, of course, we could do some experiments, yeah.
For silicon wafer dicing, normally it will be above 1 micron absorption technology will be good. So for 532 nanometer with sugar, actually, I mentioned to him the peak power density very high. That was using picosecond. But for nanosecond, maybe it's hard to process. Okay, thank you very much.
Thank you.
Thank you very much.
Have a good time in Swiss.